welcome everyone. And we are super grateful that you spare some time joining our session with Hyperflex. My name is Ploy Wongtalat Kwan. I am the marketing coordinator here at Hyperflex, and today I'll be your moderator. And we're super excited to dive into these topics. It is a topic that become huge in Elastic communities. So we want to find out how to keep healthcare data secure and easy to search using Elasticstack and generative AI. So today we have amazing speakers. First, let me introduce Vishal Rathod. He is the CTO of Hyperflex. And we have Miroslav Milehov. He is the seasoned data and AI specialist with decade of experience in healthcare analytics and enterprise platform engineering. We're going to keep this session very conversational and practical. So please drop your question, comments in the chat as we go. All right, so let's get started. All right, a little bit before we jump in. Let me quickly introduce about who we are as Hyperflex. So we are your Elastic expert. We focus 100% on Elastic, and we help the company get the most out of their Elastic use, whether we're starting from setting things up for the first time, migrating your data, or managing your cluster, so you don't need to worry about it. We are super proud of our team. We were founded by former Elasticians who actually worked at Elastics. And we now have over 20 certified engineers on staff. That means when we talk about search, observabilities, or securities, we are coming at it with deep and hands-on experience. We are global teams, so we operate from different locations. We have teams in New York, USA. We have teams in Alberta, Canada, and we also operate from Pune, India as well. And with the simple question, why people love working with Hyperflex. So it's just because we are the specialists. We only do Elastic, so we are sharper and faster at solving problems. We help clients save their operational costs by over 50% and save tens of thousands of dollars just by tuning the system correctly. And here are some exciting tools. So here is Splunk to Elastic migration tools that is exclusively to Hyperflex. So if you are currently a Splunk user and is considering Elastic ecosystems, so we are like this tool is here to help you. When you deal with data, everything is really sensitive. So we have this tool to help you automate your migrations at ease, so you don't need to worry about it. Okay, so with this tool, you can achieve 80% faster migrations with peace of mind. And here's another interesting tool. It is the Elastic Seamless Upgrade. So if you are the engineers, you know how painful it is, how difficult it is to upgrade Elastic. And Elastic come up with upgrades really close to each other. So we have this tool for you to help you upgrade from one version to another with just one click. Here at Hyperflex, we take care of all the steps, including we do the snapshot, we do the pre-check for you. So this support whether you have 5 nodes or 50,000 nodes. So now I know what you guys are waiting for. No more me talkings. Let's get started. So now I'd like to hand the mic to our CTO, Vishal. So please take it away.
Awesome. Thank you so much, Ploy. I'll quickly share my screen and we'll directly jump into the topic. So today we just want to focus on why healthcare data and the digitization of healthcare is not like any other data engineering projects that you might have seen. We have so many data enhancements going on, so many projects in finance, in personal database, but with healthcare, it is a completely different story. And here, based on our experience with working with different healthcare providers, here are a few challenges that we have noted. So the first and the foremost important challenge is the data silo and fragmentation. What I mean by that is the healthcare data and the medicine data, it is not unique. There are so many different types of data which are completely unrelated. We have EMRs, we have lab reports, we have genetics data, we have history, we have clinical notes. And still, a lot of major health providers have been using legacy SQL where your data is just sitting and cannot be used for insights generation or analytics. And the second important challenge becomes is that all of this data that we just discussed is unstructured. We cannot put a structure on what individual doctors will write notes as, what will be the history of each patient, how and when their different treatments and procedures have been done. So once it is unstructured, we do not have a control and it becomes completely unsearchable. What that essentially means is we are burning money on storing the data, but we cannot generate any insights. Unless we are generating insights, it's just raw data costing us. Another challenge that we have seen is that most of this data and the legacy SQL databases, they have a rigid schema, right? And it makes it basically impossible to ingest all of this data correctively and basically use it for any progressive things like advancing the researches. Another set of challenges that we have seen is like there are like latency when the healthcare data, as we know, is growing exponentially and we need every answer in milliseconds. Most of the queries and reports that we have seen take days or sometimes even weeks to complete, and this basically slows down any advancements or research projects that the leading organizations are doing. And apart from this, we also have infrastructure blind spots. What I mean by that is, apart from just maintaining the data, as we see the number of hospitals and clinics and all the advancements in medical tech, that is the machines that we have, we do not have a complete visibility of real-time telemetry of these instruments. So we need something which is near real time and performs under the hood for visibility of all the apps and infrastructure which are directly in touch, first touch with the patients. We also discussed like there are clinical trial bottlenecks because all a lot of research is based on how fast you can iterate and test different things. Once the legacy SQL databases slows down, the report generation is not there, we do not have proper search results, it basically pushes the research by years and sometimes even decades. And to cherry on top of everything is that if each of this solution has to be done by making sure that the security and compliance are properly met. Healthcare data and medicine data is very sensitive and needs to follow strict HIPAA and GDPR compliance. We cannot just use any tool, any solution to fill up these gaps. And with these advancements in the new AI and ML driven solutions, we need to make sure that compliances are always met. So next we'll be talking how some of the Elastic users are solving this problem and what is the impact that they are seeing. We'll be seeing some on-ground live case studies, how the research studies are being accelerated, how the end patient is getting impacted in a positive way with the use of Elastic. The first and my personal favorite is accelerating R&D in pharma. What I mean by that is, imagine the situation when COVID hit. We needed a vaccine as soon as possible. If we take a average of how much research time is needed for developing one single vaccine or one single medicine, it is usually decades of research. How Pfizer and Merck have accelerated their R&D by using Elastic. So they had decades of research knowledge databases and a very complex genomic data sets that required a lot of searching. What they did with Elastic was they created a centralized global scientific data cloud. They collected all of their researches from across the different geo locations and unified that into a scientific data cloud powered by Elastic. Why specific Elastic? Because it supports unstructured databases. You don't have to put any structure. You can just take your clinical notes, your pharma research, any PDFs and just dump it directly into Elastic. And you can perform very intelligent semantic search, vector search on top of it. You don't have to put any structure around it. You don't have to spend time just cleaning up the data. Apart from that, they also started using some of the R&D companies are using SRAY, that is Elasticsearch Relevance Engine, for supporting natural languages and that support research queries. And on top of that, vector search and RAG are also implemented to find and summarize thousands of papers instantly. The decades of research and complex genomic data has now been summarized into one single query. The impact of this has been Pfizer was able to build a central global source of truth for all the researchers across globe, and Merck was able to faster identification of genetic drivers for diseases. Every disease has been associated with some genomes, which is a very complex large data set, and Merck was able to retrieve all of those within milliseconds. Another issue that we discussed was making the EMRs and EHRs searchable. So CTQ and UCLA Health have moved all of their manual records review to automated cohort discovery. What that means is now you can just directly search on the patient data to find any relevant results that is needed to proceed further on any treatment. So EHR data is very hard to search. And a study says that clinicians spend around 40% of their time manually searching through the data. We have the best of minds who can be spending their time doing on medical research and treatments, but are now just playing around and finding the right data set. Elastic takes that away. It takes that burden on itself, and the clinicians and medical workers can now just focus on what they do the best. Also, the traditional EMR searches are very limited to their structure fields. Most of the insights which is hidden within the text of pathology reports and physician narratives mostly remain invisible. They do not show up in the proper search. So how Elastic transformed this for UCLA Health and CityQ? All of this data, that is the pathology reports and the clinician notes, were indexed directly into Elasticsearch, which took into consideration the structured EMR plus unstructured free text clinical notes as well. So now any search is being performed, it takes into the whole data into the consideration. This is powered by hybrid search of Elastic, where you can use multiple different search techniques like semantic search and basic keyword searches to go through all of your data. On top of this is privacy first NLP. That is, privacy is the first parameter, and then natural language processing. So all the clinical concepts that are there within the pathology reports and the clinician notes have been extracted in one place without data being moved out of their secure cluster. Everything is air gapped. Nothing goes outside the secure environment. Nothing goes on the internet, and everything. All the models are powered directly on their own data centers. Apart from that, it is a very fast filtering mechanism that they have built. It is almost like a Google. You can just search in a few keywords and you'll get all these sorts of patient records that you need within seconds. You don't have to wait for weeks to a report to be completed. Another challenge is like real-time public health and crisis response. So here we have a case study of Perseverant and IMS, Institute of Emergency Medical Services. So they are using a search power analytics tool to track diseases outbreaks. So what usually happens during outbreak, like a Ebola or a flu, is there are a few hotspots within some parts of the geo region. When you look public health as a whole, it is very difficult to extract these specific hotspots. It's almost like a finding a needle in a haystack, because you are in the existing traditional system. The primary limitation is the legacy systems. You cannot run queries which can give you sub-millisecond queries results on such a huge database. So what they've done is they've started using Elastic, and all of their data, whether it is CSV or HL7 compliant or JSON data, which do not have any predefined schemas, are now being ingested live, and all of the queries are sub-second analytics. Every query and reports run within a 10-second of time. And any symptoms that is found as a threat to public health, let's say there is a outbreak or sudden surge in the vomiting cases in any particular county or city, it is generating alerts in real time. In the legacy systems, it would take almost a week before we get this alert, and within a week's time, the outbreak would have spread in a lot of bigger region. So IEMS has created this real-time syndromic surveillance dashboard, which spots any spikes in any public health threats within their whole region. And now coming to something which is directly impacts the patients within the hospital or any Medicare facility, that is infrastructure reliability. So now acquired by Oracle, but earlier when they were working with Elastic, they were Cerner Health. What they have done is, so basically, if you see at Cerner, they have 27,000 facilities which monitor all the patients directly, and there are multiple different infrastructure that is associated with each of these facilities. These are critical life and healthcare monitoring tools. What they've done is they've unified their observability of all the 27,000 facilities, and they can now monitor in a single elastic stack where in which hospital which machine is performing well. There are We are basically able to detect any issue with any machine within sub-seconds. An alert is generated across such a huge stack. They've also implemented rapid RCA. What this means is whenever there is any downtime in any of the machines, if there is any issue, you don't have to wait and go see at the whole logs, and the basically root cause analysis process would take days before you can identify why this particular thing happened. Now, within a few minutes, they can identify, okay, where did the issue started and how can it be fixed. So how it is impacting the direct customer, the mean time to resolution any issue has been brought down by almost 80%. I have yet another very interesting example by Influence Health, where they are personalizing the patient journey. With healthcare, the problem with direct patient interaction is that we cannot have one size that fits all communications. Every patient, every doctor, a pair has a very different communication styles, and that needs to be taken into consideration before we make any public health based solutions. So what Influence Health has done is they have personalized their whole Medicare facilities for each patient. Every conversation and every detail related to each patient is ingested into Elastic in a secure environment. And based on the analytics on this, they create a real-time personalization. Website and apps, they can adapt directly to what the patient needs and at what stage their treatment is. Uh, Another use case is Indiana Health Information Exchange. So you see the public health and the health of a whole as a nation, it is not just about individuals, it is also about whole the public health, how it is performing. Let's say if we have a bad water or water contamination issue, it would impact the whole community. So they have created this centralized power where any research institute that needs any health related services or information, they can directly access this, and this basically powers the researchers across the globes. While we are working with individual patients, it is difficult to identify the social drivers of health. These hidden SDOHs basically do not come up in any analytics, and if they do not come up in any analytics, there is no solution. So when IEH, Indiana Health Information Exchange, built this centralized solution, they also created this keeping in mind the SDOH extraction. And now whenever new public policies come into existence, they take into this consideration. Enough about the theory. We'll also be showcasing some demos. We'll be talking about how Elasticsearch performs. And here is a brief architecture of how exactly Elastic Stack performs. So here we have the orchestration layer where we have our components like Logstash, that is the input component which collects the raw data, is running on Kubernetes. And then we have Elastic Stack, that is the main search engine and the analytics part. The beauty of this is that this all can be air gapped. Elastic provides multiple ways where you can use any external or open LLMs and directly integrate at your ingestion layer. We have Miroslav, who has a very rich experience here, and he'll be walking us through this part.
Hi. Thanks, Vishal. Thanks, Roy. So yes, this diagram is, we try to create a diagram to summarize the entire theme of the talk. And indeed, we have the external LLM providers, we have the Elastic Stack, and we have Logstash. And basically, we can use this external LLM provider, which actually can be privately hosted, to interact directly with Elastic via the ingest pipeline, which we're going to see later. Or to interact, we can move this whole stack directly into co-located with the same, next to the Logstash pod, within the same pod where the Logstash is. So summary of the talk, we will do parallel Logstash pipeline and ingestion scale. We will introduce quickly the ingest processor and the ingest pipeline. And from the enriched processing, there are some trade-offs, and we'll show some quick benchmarking. From there, we'll dive into the inference processor and how this integrates with the different LLM providers, including private ones. And at the end, we'll finish up with a Logstash, the most possibly private integration with LLM, hosted in the same pod. And we'll do some quick demos at the end. So, for the demo, which we're not going to show the ingestion, we used a benchmark data set, 9 million records from the CMS provider services. It's freely available on the internet. And for the parallel processing, since this one doesn't have timestamps, we just created a primary key. We use that primary key auto increment as a partitioning. So 9 million records, let's say divide them by 3. So I have 3 pods, and each pod is executing SQL query, JDBC query with paging against the source database. And this is basically the concept for any sort of parallel execution. Typically in Elk universe, you do that with Logstash, but can be anything else. And the idea here is that we can spread horizontally the ingestion process, split it across many parallel threads. And this is very useful when you have some natural partition key. In a real world transaction data, maybe your natural partition key will be some timestamps. Maybe your data is so huge that you have a weekly or monthly data set, or you have each index is split on multiple shards. But anyway, the idea is that you scale pods infinitely for your big data set, and theoretically you should be able to ingest your data in a very short time frame. What happens, another very neat thing, which I'm going to explain in details later, is the ingest pipeline, which is a centralized logic, which contains all the business-specific enrichment processes, knowledge related to these types of data. So we can use this enrich pipeline across many ETL jobs. Traditionally, you would do that at ingestion, at the SQL level when you have to do your lookup tables and your other business logics. But if you have many data sources in the enterprise settings, you have hundreds of tables or thousands different use cases, you need to carry the SQL everywhere versus just, let's say, have a zip code. And you always want to say that zip code having those 2 different attributes like a metro area and county and such. You can have this centralized in the pipeline. And of course, another from the documentation, from the visual documentation about the enrichment policies, we have our different source indices, which are typically static data, like a categorization of codes, zip code data, you name it, whatever specific. You can combine as many sources as you like, and as the data travels, as a part of the index settings, you have the ingest pipeline, which can perform a number of transformations on the data in flight right before it's committed, ingested into the index. You can do dissect, you can do string splits, you can additional cleanup if some other attributes are showing up. You can, of course, enrich. And later on, there is also inference processors. So we can call LLM on the fly, or some ML model for additional categorization and such. So yeah, benefit, centralized logic. The downside, it's reducing ingestion time a little and requires more CPU and more resources. So we did a quick benchmark for the reference data set with 9 million records and the 3 lookup indices. And basically, we have 2 setups. One is a single shard, and the blue lines, and the other setup is 3 shards, the same data. So the gist of this is that by moving from 1 pod to 9 pods, because you do different number of pods, we reduce, it scales linearly when you have many more shards. And for a single shard, with single pod and the 3, we have some increase, but when you go from 3 to 6 pods, it's kind of saturated. So it didn't even make sense to try for 9, because most likely there are some other bottlenecks here, probably the CPU and the disk and how much it can write. So it's not only about matter of how many parallel threads you have to ingest, but also how many shards on the other side are ready there to meet, that intake. And of course, like you said, for 1 point. Also, another comparison here, we have the top lines. These are without enrichment, without enriched processor. The bottom or with enrichment, and you see there is some shift, overall linear shift in performance. Vertically, those are ingestion. Vertically, it's ingestion rate in thousands of documents per second. So if you just look at the extreme numbers here, basically we reduce about 6 times, from 12 minutes to 2 minutes, from 1 shard single pod to 3 shards 9.6x. It is something similar. It's close to 8 times, I believe, when it comes to the enriched data. But overall, let's call it the tax on the enrichment is about 30% drop in the ingestion rate. Now, this specific use case I chose to add a lot of data fields which are not necessarily needed. I just wanted to double the amount of data in terms of columns. And this thing nearly doubled the index footprint. However, in a real-world scenario, as the data size grows, let's say it goes to 100 million, from the 9 billion to 100 million to billions, that ratio between non-enriched data and enriched data would actually shrink, because Lucene utilizes the so-called term dictionary, which is basically putting all the common values. Like imagine the lookup index basically going to go into Lucene in the term dictionary, where it will just keep pointers to the index. So in a way, it is also keeping best of both worlds in the SQL, where everything is put in a separate tables and such. Next, we'll introduce the inference processor and connect it with what we just talked here, and integration with LLM providers. So Elastic provides the ability to host your own transformer models with the data ML on the data ML nodes. Or you can also integrate with third-party models, which are, as long as they're OpenAI API compatible. This is done with the inference service, which takes one of those 3 items. It could be the inference ID, which is the external provider. It could be the model deployed ID, which is the locally deployed. Or it could be a trained model, which is a subset of the deployed model ID. The types of inferences, when you set, the inferences, embeddings of different types, re-ranking, completion, or chat completion, where completion and chat completion, those are specific to the LLMs. I just want to mention that it appears that with the newer documentation, everything now is inference ID. They don't really use model IDs anymore. But if you look at the bulk of the blog posts and use cases published by Elastic out there, many of them, they reference, because it's been going on since 2021, they reference model deployment ID. That's why I added this here. Probably in the future, model deployment ID will be not relevant anymore, but I just put it here for completeness. When it comes to which models we can host on Elastic, again, host, that means private. It is deployed on your cluster on dedicated ML node, or you can co-host it with the data nodes. Basically, all the models from the bird family, the different birds, anything from Hugging Face, pretty much you can host it. So inference integration, Elastic recently started providing the so-called EIS endpoints, Elastic Inference Service endpoints. And those are basically entry points for all the different models and GenAI providers. They also provide, to deploy in your cluster, the sparse embedding model ELSER, or the multilingual dense vector embedding E5. Those will come out of the box with Elastic. You just enable it, and no need to do any deployment. It's one-click deployment if you like. Default, you have them by default. External inference providers, basically all of the mainstream providers that we know, and we all hear all the time, many of the known ones as well, they're all there, they support them. And of course, you can provide your own privately hosted LLM. And how do you do this? The inference for OpenAI, for example, we have an example. You have the inference type completion. It could be for embedding, would be, for example, embedding, those are defined. And then this one here is the user-defined string, which helps you identify what it is. And those are the parameters. Similarly, for privately hosted model, if you have access to inference API, which you manage or maybe provided by other provider, same way, you just say the service type is OpenAI. Again, this works only for LLM providers which support the OpenAI API. And basically, here is an example with a locally hosted Ollama and a model Gematry. Gematry is I believe, the Google model. And this is how integrated. So advantages of LLM. You can do everything which you would do traditionally with the NLPs, but without the fine tuning. If I were to summarize it in one. For example, you can do also advanced categorization analytics. If you wanted to do aspect-based sentiment analysis, there aren't really many models out there, and whatever models you find on Hugging Face, they're very specific to a data set or industry. You cannot just create aspect-based sentiment analysis, which is basically have some text, and you want to identify the different categories in that text, and for each category to assign sentiment. So typically user reviews of some kind, or somebody can be saying something positive about one thing, but in the next sentence, something negative. With LLM, you just fine-tune your prompt, try different models. There are all sorts of LLM models, and it just works. I'll just point from the second bullet point here about summarization and generalization without fine-tuning. The idea here is that extractive, not just abstractive. An extractive summarization, it just copies the existing sentence directly and creates like some different version. While the abstractive, it can generate a whole new text while providing still the meaning, keeping the same sense of the meaning behind it. The abstractive generates new sentences and still preserve the meaning. And that's what the strength of LLM is, versus the traditional BERT models. They cannot do those type of transformations. So yeah, use cases again, sentiment analysis, data enrichment, if you want to have dynamic categorization, content moderation, if you have to filter out certain sensitive topics or data identification potentially. Entity extraction, which, for BERT, you need to have a dedicated model for that. Here, you can even have all in one prompt. And data transformation, which we'll see later in a demo. And the final thing I want to present is the secure same pod architecture for log stash ingestion with LLM HTTP filter. And the idea here is that in Kubernetes, in the same pod, in the Kubernetes job, we collocate our log stash with a local LLM service, meaning they all live in the same pod. And the idea for that, this is a specific use case, but from security point of view, it doesn't get more secure than that, meaning this is not exposed to the network. There is a local communication between log stash and the local exclusive LLM service. The data never leaves the pod, and you have no access to the data also from the pod point of view. And no external dependencies. It's truly private, in a sense, air-gapped capability. And this is good for the short-lived ETL jobs, where you just need the LLM to do the data processing, and then you discard it. So no persistent LLM service. And by tuning the resources you deploy for this, it can run, typically use Ollama, Modular, Max GPU, TGI, VLLM, whatever your preferred provider is. By tuning your resources, you can really have this dedicated LLM just available for you during the ingestion time, which can be minutes, can be hours, and then once you're done, you discard the resource. You can free it up for something else. And now we go with the demos. And we do the questions after that, right? We created a website with summaries and demos, and you can try some of this yourself later. The first is the 3 lookup indices that we're going to demonstrate how to enrich data with those three lookup indices. So the three lookup indices are the CBSA, which for each zip code provides the county name and the CBSA name, which is the metropolitan area. The next one is the RBCS dataset, which is basically a taxonomy with groupers for the Medicare Part B for a clinically meaningful categories and subcategories. The dataset is basically from data.cms.gov. This is the link to the dataset. We provided it also in the repository. Later you'll see. And the third one is the RVUs file. RVUs are the relative value units, which are basically represent the relative resource and complexity of given medical procedure. Basically, you cannot, kind of like adjustment factors for different kind of procedures. And basically, you create your policies, which is shown in the diagram here. The enriched policy, which would depends on a different index, source index. For each one of them, we create a policy, we execute, and at the end, we would create the actual pipeline, ingest pipeline, which we call Higgs-Pix enrichment. And this Higgs-Pix enrichment pipeline is using the three policies for the three indices. And what it does is for each one of them, basically, it is looking at two of them are based on Higgs-Pix code, and they're putting the enriched data in a target nested field, RView data and RBCS data and CBSA data, which are defined by our policies, which fields to use. That's why I was saying this was kind of like extreme example with the enrichment benchmark. And now, let me delete the index, the demo index. We will ingest a simple document, which has just a Higgs-Pix code and rendering provider zip, because that's what we have here in the pipeline. If I do this one, and now if you see what it happened. So basically we ingested a document with just two fields. And look what we get at the end. We get this giant thing, which is basically, we have our original Higgs-Pix code, we have the RBCS data, the CBSA data, and the rendering, the RView data with all the different attributes we discussed. Let me insert a couple more. This one is reading chest X-ray, I believe. And this one is actual cardiac procedure, coronary artery bypass graft. And now if you query that index with those three documents and just extract the total RView for facility, we will see that basically our cardio procedure, the RVUs are 54 versus reading X-ray is 1. Those are relative value units. And that's how, basically this works. Second demo, in inference pipeline. For example, for here I created a Cloud Opus model inference pipeline. I put my entropy key in the console. Here you have the config, which contains different variables you can refer to later. Also, this type of settings, they can be embedded in your original config, deployment if you have persistent. But for the demo purpose, I do everything in the console. And to test the joke, let's test the Cloud Opus joke. Tell me a joke about lipids. And here is the answer. Similarly, for the local embeddings, I created 2 of them. One of them is with the Gemma tree, which I called Olama chat completion Gemma, and the other one is with the 5.4 mini, which is also in the Logstash demo later on. And again, this is calling a locally hosted in my home lab here, Olama running off of GPU. Let me test the Olama, make sure it's there. Yeah, it is here, okay. The Olama 5.4. So creating the pipeline. For this pipeline and later for the Logstash demo, that's kind of like if you like even your development process to know how do you know the prompts and how to integrate with Elastic. Here we create a LLM classification ingest pipeline. For this pipeline, we're going to use the Microsoft MTS Dialog dataset, which is a dataset from 2023. It contains doctor-patient conversational notes. And for each note, the dataset assigns a clinically meaningful category. They're one of the 20 categories. Has a summary, and I'll show one of the conversations, which is basically here. We have doctor saying something. It's basically doctor-patient conversation. So we create the prompt, which says, summarize this doctor-patient conversation, one of the 20 meaningful categories, yada, yada, yada. I'll put a JSON, and I ask the JSON to match the keys to the one of the data set. But we're only taking the conversation and we're analyzing it. I created two pipelines. One is using the local Ollama. The other one is using the Anthropic. Everything else is the same, just the different models they use. And basically, here are the other processors. For example, we remove some fields. Once the LLM hopefully generates actual proper JSON, we have a JSON processor which will try to convert that string into JSON and put it into JSON target. If the process any here fails of the previous, it will route the request to document which is called failed dash the index name that we're ingesting when it comes to ingestion timeline. And let's test it. Here is also the Anthropic pipeline, the same thing. So here is the first one with the local Ollama classification. When you call that, and here is generated text, here is the section text, and the header is 11 assessment. So basically, this is the summary, and this is this one. Let's get another one, which is shorter. And you notice these two, they all executed because this is against local LLM in 200, 300 milliseconds. Let's see this one, 260 milliseconds. Now, if you do the same request, but against the Anthropic pipeline, which is somewhere far, far away, that always going to be seconds, most likely here, 2.5 seconds. Let's see this one here, the previous one. It's 3.3 seconds. Let's do it again. Still 3.67 seconds. And I even chose another example, which is the longest possible prompt I could find in that doctor conversation, which is ID number 31. And let's see how those two compare. Here is Ollama, locally hosted. 350 milliseconds, 500 milliseconds, 300 milliseconds. We're doing sort of a benchmark versus Anthropic, which will be probably something of the order of 5 seconds, I would say. Let's see. Running. I'm looking at the bottom right once again. This is 6.5 seconds. Let's do another one. That's the same request to Anthropic. 6 seconds. Again, versus local one, which is I just call a different pipeline by changing the string to which pipeline I do. This is a simulation of the process. There you go. 400 milliseconds, 300, 400, 400, 300. I mean, it's basically 10x improvement in a way. Well, it's a different question. What if you have multiple threads? That comes down to, because now who is hosting, who is managing this? Who would manage your local LLM service? But here is another advantage, apart from the privacy, that your LLM being close to where your processes are, meaning being 1 millisecond away, and you manage the resources. I mean, this is the advantage. And Elastic supports this natively. And for the final demo, I'll just show the repository and I'll do a quick run. We created, so once you have this prompt running, you like how it works. Now you can use this in another settings where for the same data set, we created a simple job MediQA in all the files in a single, for easy readability and demo. Typically, this will be split across, different, customized with config maps and everything on its own folder and such. So basically, Logstash YAML, because the demo is on a CPU, I explicitly can tweak the configuration to be single worker, one batch size. So only one request in flight because of local CPU model. You will tweak this later when it comes to production. The input, a Logstash input is basically reading the same file, the MediQA chat 2023, which is basically literally this file. And it is a multi-line parsing, and I tried first to create this with native Logstash filters. Unfortunately, this CSV has all sorts of not irregularities, but inconsistencies. So Ruby was the easiest way to really parse this multi-line because there was a double quote, triple quote, without quote, multi-line, different carriage returns. So basically, I had to go with Ruby to be able to successfully parse all the 200 records in this demo dataset. And at the end, once this LLM generates the JSON, another thing about the LLMs, and when you ask it to generate JSON, I've seen this a lot, even with the commercial, the big name providers, it happens that once in a while, they would not generate a proper JSON string. Even though you extract it specifically, do not put any markdowns, any JSON. It will still put some extra stuff around the JSON. And when it comes to those native processors, like in Logstash or Elastic Ingest Pipeline, which expects JSON strings, it cannot parse it because it didn't provide. And that's why even at the final stage here, I have a Ruby pipeline to get the JSON string properly. And at the end, we just parse it somewhere, store it somewhere. This is the part which is extracting the JSON. And at the end, we just put it on a file. Now, this is a demo purpose, locally hosted Kubernetes. So the data, the input and output, they're on a PVs, locally mounted storage part of the container, so for easy reusability. And when it comes to the pod, there are 3 containers. First, you have the initial container, init container, which picks up the model, puts it in the shared volume, which is dedicated for the Olama in this case, to store the model. So for when you run it later, you don't do another 2, 3, 12 gig model download over the internet. You have the same volume reused if the model exists. And then let me just show them. To the machine which hosts the mini Kubernetes. Here is the mini cube with Olama namespace. There is nothing there. And I will execute now this file which I just shown in the MediQA YAML. I already created the PVs. And this creates the job. Here is the 3-1. The first one is downloading the model with Olama pool. It's already there, so it was very quick and terminated. Next one is our Olama, which is starting the service right now. I believe you can see that. Yes. And already I can see 7 seconds, 2 seconds, our Logstash in flight is calling the model for each line processing. Here's the processing in the output. Just want to show you basically. So this is running on 6 CPUs, and you can see it takes about 7 seconds, 2 seconds, 5 seconds per request for this type of data to process on CPU locally. In a real production world scenario, you would actually probably use some GPU node to execute this on GPU. But for the demo purpose, it's pretty good and doesn't get more private than that really. Here is I have, because this is Minikube on Podman, and Podman does not really have a virtual machine, I can even see the 6 Olama processes running for the, basically on the bottom here, we have the processes for this job. And now once this thing finishes, this architecture, a Logstash at the input, it has a section which says terminate after completion. Let me find it where it was. But it is basically exit after read. So this will kill the Logstash process. There is also shared processes name. So Olama is listening for Java. Is once the Java Logstash terminates, Olama listener also terminate the pod and the resource get freed up based on some configured time. In this case, I set it to 5 minutes. And with this, I believe concludes my demo part. And open for questions now.
All right. Thank you so much for Vishal and Miroslav for covering all of that. The insight was really interesting. So now it would be time for questions. I see a couple interesting question comes up in the chat. So, and I see that a couple of that have been answered by Vishal already. Thank you so much. All right, let's go back. But however, we would like to discuss this here as well so we can understand things better and you can explain it better as well. So first question is, does ELK performing any pre-indexing to faster schema on read system reading pace?
Mhm. So I can take that question. I think there are multiple ways to do it. So if you look at the whole data journey in within the Elastic Stack, so the first layer, that is data harvesters, right? Agents, Elastic agents. You have multiple pre-processors there that you can use. Or at the ETL layer, that is the Logstash, where we do the heavy lifting of the transformation and reading and cleaning the raw data. There you have multiple ways of defining the schema, what particular field should be in what data type. There is, and the final layer is directly at the Elastic cluster, where we have dedicated ingest pipelines where we can define the data types, extract some, do some basic transformations. So this typically helps. There are ways, like if you already have a schema defined, you can define your own schema, that is index mapping. Based on that, you can also like have a faster schema.
Awesome. Sounds good. That's really helpful. All right, next question. The LLM lives in the same pot of Logstash. Is there any doc to scales or to know how to scale it?
Uh, uh, Maybe Miroslav can add, but my experience is it is better to use a separate compute unit for your LLMs. You can have extra pods. Having it in the same pod is not production friendly architecture, I would say. Coming to the scaling part, I think there are multiple benchmarks that you can do. There is also LLM monitoring that you can perform, and based on how much tokens you need and how it is performing, what's the latency like, based on that you can scale it up and down. So like Miroslav mentioned, scaling is basically, there's no limit to it how much you want to scale. Based on your use case, you can scale it.
Yeah,
Miroslav, do
I
you?
just wanted, it's not automatic. You need to benchmark it up front to see what the actual compute needs, and then you provision the right amount of resources to complete the job at the desired time frame. So there's no like auto scaling in terms of Elastic. Basically, you scale it on demand based on, oh, I need more resources. You need to determine this upfront. So in a way, it is static, and this is a job which everything is predefined upfront. How many pods, what kind of resources, how are they? So in a way, there is no scaling once you start the job. You need to do this upfront work for that. And again, it's a specific use case when not it's for short-lived ETL jobs with really private LLM.
I see. Yeah, thank you so much for adding that and also providing a use case as well. That's really painted pictures of how it's supposed to be. Next question is quite long, so if you guys want to jump into the chat and see, following as I read. So he has a question regarding elastic feedback loops in search cases. These AI systems continuously retain their models using the Elasticsearch and analytics pipelines. With these feedback loops, what are some ways to avoid automation bias or errors? I'm curious about how this occurs as physicians adapt their works to the output from your models. Thank you.
I think this is a very on-ground question, and it's a very interesting one because let's first understand what the echo chamber impact is. So let's say my model is giving me a slightly less accurate result, but it is ranking them at the top. And as my users, prefer the first top ranked results, it creates a negative bias, because even though the result is not accurate, but it is getting the most clicks. So to basically to fix this, we have this rank evil API. What it basically will do is, instead of training on the CTR numbers, we can have some expert weighted results who will now create a sort of judgment set for my model. So based on this, we keep correcting our trajectory for the correct results in improving the accuracy via a expert weighted solution instead of just sticking in the CTR numbers. So using this, basically this is also used in e-commerce. So to basically we are taking the user input, that is CTR numbers, and the a human provided judgment set as well. So combination of this basically solves the echo chamber impact.
Cool. All right. And he has a follow-up question after that as well. So he's asked, like, how do you make sure that the rankable judgment will not get biased as physician adapt to what Elasticsearch layer ranks over time?
Yeah. So like I mentioned, using a
Mhm.
human-based judgment set, we can fix that.
I see. All right. Yes, I think those are all the questions. Thank you so much, everybody, for adding those questions. It makes the session really engaging, super interesting, and we have more insights out of the slides as well. All right. Last thing here. So I would like to take a moment to thank you everyone for joining our sessions. Us as Hyperflex, we're hosting monthly webinar every month. We also have the Kibana series where we show you how we implement Kibanas for data management and data visualizations. All right. For any follow-up question, inquiries, feel free to email us as marketing@hyperflex.co. And also for any other question about Hyperflex, feel free to learn more about us at our website, Hyperflex, www.hyperflex.co. And also, we post our news and any updates regarding webinar, anything about Elastic, anything regarding any tips or the content there on LinkedIn. Feel free to connect with us and make sure that you stay tuned for the next upcoming webinar. All right. Thank you so much. I would love to take a moment to thank our speakers as well. We learned a lot, and we're sure that all the attendees also walked away with a lot more insights and knowledge about Elastic GenAI in healthcare. All right. Thank you so much, everyone. And I hope to see you guys in the next webinar. Thank you so much.